Our second speaker is Vijay Kanamuri from Renaissance Electronics, where he's a senior principal. 16 years of experience in leading design verification teams across SOC Design Verification, Platform IP Design Verification, HSIO, Networking, Infrastructure IP domains in Texas Instruments. Has been instrumental in developing a platform methodology for verification across multiple product lines, as well as leading end-to-end SOC DV execution for successful automotive ADAS SOCs, including post-silicon test development. And the title of his talk, and he's going to speak for 15 minutes on challenges, and his challenges are in verification for automotive applications. Okay.
Good morning, everyone. Can you hear me?
Yeah.
Okay. Hi, my name is Vijay Kanamuri. I have worked in Texas Instruments for automotive SOCs, ranging all the way from MCU all the way to SOC. I'll start with overall use cases. If you just look at where the industry is trending, what are the challenges that we are seeing, and kind of overlay that with what we need to do in verification. If you don't plan that well, what typically happens is you're late, your schedules are late, you find issues late, and that's how we get into issues where you're thinking about feature descopes. So just think about cars 5 years back or 8 years back to where the cars are now. Backup camera, you almost have like a 1K display. You have a lot more ADAS functions, which is your front camera, or it could be radar or LiDAR based automatic braking systems. And at the same time, you have your car. Imagine your Texas heat and you're having your car, you need a low power SOC. Power becomes very critical because you don't want liquid cooling in your car and the cost goes up. So when you start looking at the verification and how those use cases map, you have a lot more data in your car right now. 1K frames, maybe 30 frames per second. And your backup camera, or even smaller, you have a lot more data. You want to compress your data, you want to store your data. And after that, based on the data, you want to make decisions, whether you want to do automatic braking or lane assist in your car. And at the same time, power. And all of this has to be encapsulated in a safety mechanism, because you make a wrong decision in your car, it is a fatal scenario. So I'll start with safety and compliance. This is where most of automotive challenges are, because even though you have your high performance as well as your safe low power, everything has to be encapsulated. There is a standard for automotive, which is ISO 26262. There's multiple aspects of ISO 262, but for the certification context, I'm going to talk about the verification aspects of things. There are three main aspects. Apologize if too small. There's just a lot of information here. One is traceability. When we define an SOC, whether it's an infotainment or an ADAS or an MCU class domain controller, you have a certain requirements that are market requirements that the marketing team comes up with. Then you break it up into system requirements, which is how much performance do you need, how much bandwidth do you need, what are the real-time implications, what is my boot time going to look like. And after that, it comes into hardware requirements or product requirements or software requirements. Everything needs to be traceable all the way from the top, what are your marketing requirements, all the way down to the bottom, as well as the other way up, saying that what are my hardware requirements, how does that map to the overall use case. So it's a two-dimensional matrix to make sure that at the end of the day, you're covering all the requirements. Take an example. Let's say you want to write a USB, the requirement says that it's a software requirement that says my USB software has to run on a particular A core. Okay, that's a software requirement. How does that apply? For most of the software requirements, or 90% of them, you always have underlying hardware. Your USB controller has to be accessible from that particular core. Interrupts have to be mapped. Both your data and configuration have to be mapped. So your verification, you need to make sure that the underlying hardware requirements, even if software comes in much later, the underlying hardware requirements are verified. So one requirement can spawn into 4 or 5 hardware requirements. Sometimes it's explicitly mentioned, sometimes it's not. And in some cases, you might have a controller that doesn't support, if you break up the transactions, it requires a transaction in certain size. So at the start of the project, the planning is very important. When the requirements come in, you need to make sure that your system sit with the systems team, software team, understand how those requirements map to hardware. It's no longer going from spec to verification. You have to start thinking requirements to verification, having spec as one of the inputs. A lot of times we have seen issues where the requirement is there, the spec was wrong. How do you catch that? So, and if you don't plan this well, when most people talk about traceability, it always comes in as post-silicon. Once your SOC comes, your certification is a few years out after SOC. You start doing it, you don't plan this well, you start finding all sorts of issues. So methodology plays a big part in it because you want to automate. If you don't automate, you're sitting and writing Excel sheets, which is not fun. And that's a huge cumbersome task, manual task, which is not useful in terms of methodology improvements. And the other thing is any tool that you use has to be certified. And right now we have a lot of tool vendors that are automotive certified. There is a process to make sure that when you're getting releases, updates, you're not breaking stuff that was there previously. So making sure that you're using the right tools and planning for how you go to certification is very important. So that's covering the requirements part of it. And most of your applications are going to have some safety mechanism. That could be your ECC, that could be parity, that could be redundancy built into it, that could be lockstep. You need to prove that eventually on the gate level. The standard, if you're especially going for an ASIL D or a C, requires you to actually do a fault injection and prove that whatever mechanisms you have put in place, whatever analysis that you have done, which is your failure mode analysis, you need to make sure that you can hit the coverage that you claimed. Now, this is a very cumbersome process. It's not easy. Anyone who has done verification, the amount of time you spend on coverage, just trying to do that at a gate level, at AND gates when you don't understand what the logic is. That's the complexity here. So it's very important to make sure that you identify test cases that are targeting your safety mechanisms, and also to make sure that you have a good mapping of RTL to gates, working with your PD engineers to make sure that you don't optimize your safety logic or hierarchies. This is very important because you might have a bigger hierarchy where a certain portion of the logic is safety. And if you don't identify that and you do a flat synthesis, you're going to lose a lot of the data. And after that, you don't know how your safety mechanisms are going to apply. So logical hierarchy preservation of safety mechanisms is also important. It's higher area, but that comes with the cost of how fast you can close on safety. Okay, we talked about performance. You have a lot of data coming in. Typically, when we start doing verification, it's always point to point. Okay, our verification mechanism would be, yeah, I'll have a camera data come in. It needs to go to DDR through a controller. Am I meeting the bandwidth there? Yes, in an isolated use case, most of the time, by the time you tape out, you do hit a good bandwidth on an isolated case. The challenge becomes when you have DDR as your bottleneck and you have NOC, a lot of the bus fabric that converge. We have multiple applications coming at the same time. You have compression, you have display, you have GPU, you have video, all coming through the same pipe. That is not modeled well. So this needs to start from the architecture phase. We have tools available to do architecture analysis and make sure that your DDR efficiency, the throughput and everything meets the spec. For a particular use case, you really need to model with your bus fabric setting. Let's say your video is 1 gigabytes per second and your display is 10 gigabytes per second. You need to be able to model that with the accuracy to make sure that you don't have any bottleneck on your bus infrastructure. And coming to verification side, we either use the EDA tools or you have built-in monitors. Depending on what bus fabric you have, you need to be able to use the different tool sets to make sure. And right now, ED tools have advanced so much that you can get average latency. What is your longest pole? What is your long pole? And with use case traffic, all of these are very high performance. You are going to run into long run times. So you need to have a mechanism to be a black box, make sure that you can verify the minimum impact. Along with that, I think the built-in performance monitors and real-time come into picture in the same mechanism, where you have the BFMs and EDA tools to flag errors whenever there is an issue. One thing that always is not done is either you do high performance or real time. You also need to have a good architecture analysis of real time combined with high performance. You have your AutoSAR software running real time with displays going, and most of these high bandwidth hog the bus, and you can't get real time data or don't have a dedicated path to real time. You're going to miss real time deadlines, and that becomes very important. Low power, I think power is a concern for all, not just for automotive. So a lot of the times what we see is we have a lot more power domains because power is so critical and you don't have active cooling. It's very critical that we have UPF aware SIMs early in the design cycle. This is where you start seeing a lot of issues where things propagate. There's a lot more asynchronous crossings because of the different use cases. You're thinking about a CAN controller, which is a few megabits per second, to your camera and displays, which are a few gigabytes per second. So there's a lot more traffic that you're mixing in as part of your domain controllers. And the other thing that is very important is generating waveforms for your power analysis early on. A lot of this typically is done in emulation, whether your performance analysis or low power, and that's too late. So we can discuss a lot more in terms of over the course of the next few hours during breaks. If you have any questions, there are tools, methodologies, how to get this done. This is a spec we need to verify it. You need to start from the requirements, understand the use cases, and drive all the way to tape out. So I think that's.
Okay, thank you, Vijay. Thank you.